thumbs up பண்ண சொல்லு. என்ன கிளியரா இருக்கானே.
Please let me know if the board is clear to you. I think we need a light. Is the board clear to you? You can raise your hands like this or put it like this so I will understand. Or shall we unmute everyone for some time? Because shall I unmute? Okay, they have shown now this one. Okay. Is the screen clear and visible? Or shall I close? If I keep close, I think not able to see. We need little light, I think, which I will arrange. Okay, just a moment. Let's see if it is okay. Is the board okay to you all? No, it's light. Light we need. Charging खत्म है क्या? Make it light with a light bulb. Okay, it's fine. He says okay.
Okay.
Let me arrange this light, a little bit of light on the side. Okay, we'll keep talking. Okay, see, in the last class we studied about the Rayleigh and gene, isn't it? And gene's derivation of the Planck's radiation law and the explanation that they have given. I hope you have seen the previous video that I sent it regarding the Rayleigh and gene. Hope you have understood it. Okay, we are going to similarly derive another derivation which was explained by Max Planck. Okay, a slight modification, but major things are remaining the same except for the change in the energy of the oscillator. The determination of frequency part is same or similar to that of what Rayleigh and gene have tried to derive it. Okay, now without repeating again and again the same thing. Okay, so we will move on to the calculation of the number of resonators per unit volume. Okay, which is lying in the frequency range of nu and nu plus d nu. Okay, similar derivation. If you have gone through that video, it will be really clear to your previous one. Okay, so here Max Planck also considered the same cubical structure, a cubical enclosure in which of length x is equal to 0 to x is equal to a, he has taken it. Okay, and then he has taken that he has assumed again in the same way that electromagnetic radiations are the black body radiations are traveling, okay, along x, y and z direction. This time he has taken it majorly along x and y direction. Okay, but previously, like the previous one, let's assume that the walls are non-conductive walls and this enclosures are a non-conductive enclosure. Yes, non-conductive. Okay, now, okay, you know that when the waves are traveling, they will undergo multiple reflections from the walls, isn't it? Okay, they not only travel but also get reflected from the walls. These were not taken into account in the previous case, but Max Planck considered all those things and he said that interference takes place. Okay, it can hit the walls, okay, and then it can again form a okay, the walls can get the black body radiations. When it strikes the wall, okay, it will get reflected, okay, from the walls and they can form interference patterns. Some can be constructive, okay, some can be destructive. Okay, You know the conditions for the constructive interference to take place and also the destructive interference to takes place. Okay, so imagine such a condition when there is an incident wave getting reflected back, and then it forms an interference with the incident and the reflected wave. Okay, it is a similar case as that of the vibration of a stretched string. Okay, in your class 12 you must have studied about the conditions about the interference regarding the vibrations of a stretched string. Okay, if you have doubt in this, okay, please go through this. Okay, in your class 12 you must have studied vibrations of a stretched string. We are going to use the similar analogy. Okay, we are going to use a similar analogy for this. Okay, so as you know that once there is an interference happening, there will be nodes and antinodes. Okay, nodes and antinodes will be formed on both the sides, isn't it, in a stationary wave pattern. Okay, so imagine that there are some stationary waves which are forming in between this region. Okay, as we discussed in the Rayleigh gene also. Okay, similar case is happening here. Okay, and we are going to use the conditions of a stretched string enclosed between a container. Okay, now let us consider if L, assume that these waves are like a stretched string. Okay, these are equivalent or considered equal to that of a string. Okay, with a length L. Okay, so imagine that the waves enclosed between these two regions are having the length L. Okay, so let L be the length of the string. Okay, let L be the length of the string. This black body, radiations enclosed between the containers are considered to be having the length L. Okay, and also you know that the maximum one will have a wavelength of lambda, the next one will have lambda by 2, and so on. The conditions which I explained already. Okay, because these are considered as waves with a wavelength of lambda, with the value of lambda. Okay, so so relating the wavelength and the length L, okay, we get an equation. Lambda is equal to the wavelength of the black body radiated wave, okay, with the wavelength of lambda, entire wavelength of lambda is equal to 2L by N, okay, where N is equal to 0, 1, okay, 2, 3, etc. up to up to infinity. Okay. Now this equation is in the form of wavelength value. Let's put it in terms of the frequency nu. Okay, so substitute for lambda is nu is equal to c lambda, na? Nu is equal to c into lambda. So using this equation, nu is equal to c by lambda. Then using this equation, you will get, okay, c by 2L into N. Okay, or I can put this as N into C by 2L. Okay, so this is the equation for the frequency. Okay, so wavelength lambda is equal to, block it, don't have to worry about the notes, I will forward it later on. Lambda is equal to 2L by N, nu is equal to NC by 2L. Okay, where N is equal to, again, it's not 0, I think it starts with 1, 2, 3 up to infinity. When nu is the speed of the waves here, okay, not the light, here it is the wave. Okay, now every allowed frequency, okay, in terms of frequency I'm talking here, okay, we are going to deal majorly with the frequency part over here, not the wavelength here. Okay, now these are the frequency with which the waves are traveling, and every frequency okay, is called as the mode of vibration. Okay, so I will put it as, now we will deal it with respect to the frequency in the case of Planck's, and every allowed, okay, every allowed frequency, okay, which satisfy this entire stationary wave condition, not all the waves, okay, those waves uh, which are obeying, or I can say which are satisfying this condition of the stationary wave, are called as the allowed wave with a frequency, okay, which are called as the mode of vibration. Okay, these vibrations are alone taken into account, not everything. Okay, these are the allowed frequency which are alone considered as the mode of vibration here. Okay, this mode of vibration inside a cube, okay, can be equivalent to the string case. Okay, is equal to the string case. So as I said in the previous class, let's take the condition of the waves that are traveling along the x direction, y and z direction, and also between the x and y, between the y and z, and between the z and x direction, with an inclined angle of alpha. Okay, in terms of cos alpha, we are cosine terms, we are going to take it. Okay, so let's come to the equation directly. Okay, so here I will say the three intersecting edge of the cubes, this we already know, isn't it? X, y, and z. Well, these are the three x, y, and z axis. Okay, and these are and let cos alpha, cos beta, and cos gamma are the direction of the cosine direction, or I can say the direction cosines of the direction of propagation, okay, of a particular wave. We are going to consider a particular wave, okay, and then their projections, okay, on the direction of the propagation of the wave in a cube. Okay, so we are going to take it, and only those waves which will be allowed, for which all the faces of the cubes form a nodal plane. Okay, wherever there is a formation of a nodal plane, means the wave has to end with a node region, not an antinode region. Okay, whenever the waves are ending with the node regions, those waves are considered and other waves are not considered. Though sometimes the waves can end with an antinode or half antinode, or like this, different ways it can end. Okay, those waves are not going to be considered. Only those waves which has a proper nodes between the two ends are going to be considered as the one for this particular case of study. Okay, understand? So the allowed wavelength have to satisfy the three conditions. Such waves are considered, and those allowed wavelength, okay, have to satisfy the three conditions of equation 1. This is equation 1. Okay, and then let's go ahead with this equation. Okay, so therefore let the allowed wavelength, okay, let the allowed wavelength, okay, for those waves, okay, which has the nodal position on both the sides, those are called as the allowed waves with a particular wavelength. Okay, so such waves which are traveling along the x direction with an angle alpha, okay, is given as 2a. All those waves which are in those directions, okay, are n1, and those along the other directions are lambda 2 is equal to 2a cos beta by n2, okay, and also lambda is equal to 2a cos gamma by n3. Let's put this as equation number 2. Okay, this one is the first one, this is the second one. Okay, where here n1, n2, and n3 are integers. Okay, I'll put it as n1, n2, and n3 are integers. Okay, So this condition also we have already studied in the Rayleigh genes, isn't it? The same thing only. Okay, no changes up to this. Okay, now as we did in the previous class, let's square this equation and add up on both the sides. Okay, one. Okay. So now let's add up and square it. So take up all these equations. Okay, you will take n1 square lambda square by 4a square. Okay. Cos square alpha plus, okay. Next one is n2 square, okay. Lambda square by 4a square. I'm squaring on both the sides, okay. Here it will be plus n3 square lambda 3 square by 4a square, okay. Now add up all these things, okay. Take is equal to 1 on one side, okay. Now take up all this, this one. So n1 square lambda square by 4a square, okay, is common in all the cases. So I'm taking it out. So cos square alpha plus cos square beta plus cos square gamma, okay, will be equivalent to 1, okay. So this, will become 1. So n1 square lambda square by 4a square is equal to, on the left hand side you have 1, isn't it? So we are interested in finding what? Okay, let's, okay, n1 square. Oh, you need to take n1 square, n2 square, n3 square also outside all the cases. Okay, I think the previous one we did. n1 square plus n2 square plus n3 square. Okay, these are all n1, n2. Sorry, this is n2, n3, so we cannot take it out. Now we need to take the being 1. Already this will go. So we are left with this one will go, isn't it? So I'm removing this again. So we are left with n1 square lambda square by 4a square plus n2 square lambda square by 4a square. Actually here cos and cos has to come. Okay. So n3 square lambda square by 4a square. Okay. Now take n1, n2, n3 outside. So n1 square plus n2 square plus n3 square is equal to, take the other terms on the other side, okay. It will become 4a square by lambda square, which is common. 4a go to the numerator on this side, lambda will come to the other side, okay. And now all are square again on left hand side and right hand side. So again simplifying this equation, okay, you will get, okay, let me remove the let me simplify this equation. Is equal to, okay, this will become 2a, I think gamma 2a by lambda, the whole square. Okay. Now remove the squares on both the sides, okay, or you can now take it in terms of the frequency, okay. Lambda is going to be again changed in terms of frequency, c and nu on the other side, okay. So now we have come up with the equation. Earlier it was in the wavelength form. Now I've replaced it in the form of frequency because we are interested in frequency in the Planck's hypothesis. So let me put this as equation number 3. No, already, yes. this is, they have put it as equation number 4. Since equation 3 was cos square alpha, cos square beta plus cos square gamma was considered to be 1, which is the equation 3. Okay. Now I put this as equation 4. Okay. Now this equation, okay, will give you the allowed frequency inside a cube. Okay, this equation will give you the allowed frequency of the wave, of the black body wave traveling inside the cube. Okay, this can also be called as the total number of modes of vibration. Okay, which I can call it as the total number of modes of vibrations possible in the set of, again, vibrations are possible sets. I can put it as n1, n2, n3. Okay, and the number of modes of frequency within the, now we are, see, this is the allowed frequency, right? This is allowed frequency, and we need to calculate the total number of modes of vibration within a particular cross-sectional or particular volume, and we have to calculate. Okay, so to calculate that, as we did in the previous class in Rayleigh and Jeans, we need to take a spherical region and then draw two concentric circle, and this was the method that was done by Rayleigh and Jeans. Here we are going to now take it in the two-dimensional form instead of a three-dimensional aspect. In the earlier case, it was taken in the three-dimensional. Now we are going to take a two-dimensional one in this case. Okay, so now our aim is, this is our first aim, as to calculate the allowed frequency. Okay, this is the first one, to calculation of the allowed frequency. Now this will be drawn in a two-dimensional. It is equivalent, or I can say, let us first consider the mode of vibration in a two-dimensional phase. Okay, so I'm going to take a two-dimensional case, means instead of n1, n2, n3, I'm going to take n1 and n2. Okay, n1 and n2 is also equivalent to the same equation, for your information. Okay, so instead of n1 plus n2 and plus n3 is equal to this one, I can also consider as n1 plus n2 is equal to, okay, in two dimension, I can say, in a two-dimensional case, okay, even n1 plus n2 is also equivalent to 2a nu by c the whole square. This is also same. Okay, so we are going to now consider a two-dimensional problem. Okay, so let's put this as equation number 5. Okay, the equation that we derived is for three-dimensional, but even in two-dimensional, this n1 plus n square is equal to n2 square is equal to 2a nu by c will be valid for a two-dimensional case. Okay, so now we are going to take a circle and represent the x-axis and y-axis. Okay, so this equation represents a circle. Okay, this equation represents a circle of radius. This is the radius. Okay, okay, of a circle. Okay, we are going to take it in a two-dimensional. So imagine that you have a circle in which you have a radius with the x as n1 and y as n2. I hope you are able to understand. Let me repeat. We are going to consider the equation that we derived as equation 4 is for the three dimension, with n1 representing the x-axis, n2 representing the y-axis, n3 representing the z-axis. Okay, that was a sphere that was considered in the previous case of Rayleigh and Jeans. Okay, it's an entire sphere. Now we are going to consider a circle with two dimension with x and y axis alone. So let that x axis be represented by n1 and y axis be represented as n2. Okay, values, And let's take this as a radius of a circle. So with this parameter of x value, y value, and the radius, let's draw a circle, imaginary circle. Okay. So the circle will be with this. Okay. Let me draw this. This is the x-axis, this is the y-axis, and this is going to represent, as I said before, x will be represented by n, this will be represented by n2, okay? And let's have quadrants, okay? Let's assume that we have a quadrant, okay? And the radius of the circle, as I said, the radius will become what? 2a nu by c, with the radius value is equal to 2a nu by c. Okay, that means this will be the value of 2a nu by c. This will be equal to 2a nu by c. Okay, with this, let's draw a circle and plot. Okay, for a given value of nu. Okay, for a given value of nu. Okay, let me plot it here as points like this. Okay, so this will be 0. This will be 1, 2, 3, 4, 5, 6, 7, 8. Okay, it will go up to 10. Similarly, here also it will be like a checked ones. Here also 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, with this, with the 10 and 10, I'm going to draw a circle like this. Okay, so if you draw the quadrants, now the points on this circle, what does this represents? The points on the circle corresponds to the frequency nu. Okay, the points, each points. Okay, the points on the circle. Okay, on the circle corresponds to the frequency nu. Okay, while those lying inside the circle corresponds to frequency. Okay, the points lying on the circle, whatever the points that are lying on the circle. Okay, on the circle and inside the circle is different. On the circle corresponds to the frequency nu. Okay, for those circle, battery is low. Okay, for those, okay, I'm underlining the word, the points which are lying, okay, on the circle. Okay, whatever is the point that are lying on the circle are supposed to have a frequency, okay, less than nu, which are supposed to have a frequency which is less than nu. Okay, okay, corresponds to a frequency less than, frequency less than nu. Okay, the points on the circle corresponds to the, okay, sorry, the points on the circle corresponds to the frequency nu, whereas the points, I will write it here or here, the points which are lying inside. Okay, these are the points which are inside, these are the points which are lying on the circle. Okay, because it ends at the nodal position, so those frequency are full entire frequency of nu. But those who are having points which are lying inside this circle are expected to have a frequency, okay, which is, while those lying inside the circle corresponds to those lying inside the points inside the circle, okay, inside, underline the word inside the circle, is expected to have a frequency less than nu, okay, is having a frequency less than nu, okay, less than the frequency, okay. These points have to be noted. Those are lying, the points which are lying on the axis are corresponding to the frequency direct nu, whereas those points which are lying inside, okay, these points are expected to have a frequency which is lesser than nu. Two concepts are coming here. Therefore, okay, and every point of intersection like this is supposed to have a square, okay, is associated with a square, and the area of each square is considered to be unity, okay. Now we are going to have an equation that the number of squares is equal to the area inside the quadrant. This you know the relation, isn't it? The area of this part of the circle can be calculated by calculating the number of quadrants, okay. Therefore, I'm going to use this relationship now. Okay, shall I rub this one? The area of this checked portion can be obtained by calculating the number of squares. Virtually you can calculate and do the calculation of finding the area of the circle here, okay. So I can say the number of the square is equal to is equivalent to the area inside the quadrant of the circle, okay. Number of square is equal to area of the quadrant of the circle, okay. Keep this relationship, okay. Now with this idea, we are going to now calculate the number of modes of vibrations, okay, within the frequency of nu, which are lying on the walls or the entire ones, or which has a frequency of nu plus d nu, okay. So I will write this equation again. Now with this background idea, we are going to calculate the number of modes of vibration. This way of calculation is slightly different from the way that Rayleigh and Jean calculated, okay. So the number of modes of vibration, okay, within a frequency interval of nu and nu plus d nu. A small, again, a portion is being taken, okay, is equal to the area in the positive quadrant, area in the positive quadrant lying between the two circles of radii, okay, 2 nu by c and 2a nu plus d nu by c, okay. Like as they did in the previous case also, draw two concentric circles, okay, with the I hope this is clear to you, okay. The number of modes of vibration within the frequency interval of mu and nu plus d nu is equal to area inside the positive quadrant lying between the circles of radii 2a nu and 2a nu plus d nu, okay. Now it is like equivalent to the same one, okay. You have a circle like this, okay. This is one quadrant of the circle, and in that take two concentric circles, okay, of frequency nu, okay, with the points if it touches the points, it's all having a frequency nu. Okay, when it touches the quadrant points exactly, it is supposed to have a frequency of nu. Okay, when it is lying in between this region, it is less than the frequency nu. Okay, now draw two concentric circle like this with the frequency of nu and another one with the distance of d nu. Okay, so what are the quadrants that are lying between these two circles? That volume has to be taken. Okay, so take these two circles, take the frequency, the first one as a frequency nu, the second circle with the radii of nu plus d nu. Okay, the first one being the radius with just 2a nu, the first one, okay, by c. The second one is having a frequency of 2 nu plus d nu by c. Okay, now we are going to find the difference in the volume between these two regions. Okay, so let's take the area, as we know that the formula for the area calculation is 4 pi r square. Okay, the r is now here the two concentric circles, one with the radius of 2a nu by c, another one having the radius of 2a nu plus d nu by c. That is a two radius value. So r value has to be r1 square, rather I can say r2 square minus r1 square. Okay, two radius have to be subtracted. Okay, so it is, I can say, there are two circles, two concentric circles having two radius. So let's find the difference, as this is a radius of the last circle I have said, nu plus d nu by, okay, c, the whole square. This is one radii minus the other radii is 2 nu by c. Okay, the difference of these two is 4 pi r square. That is r1 square minus r2 square. Okay, now if we square this equation and simplify this equation, okay, let me take this. This will be, sorry, it's going to be 1 by, because this is one quadrant, right? This is just one quadrant, so I'm going to put it as 1 by 4 pi. Okay, sorry, 1 by 4 pi of this one, because in a two dimension I'm just taking the one quadrant portion only. Okay, so because of that, this formula is 1 by 4 pi of this equation. Okay, now if you really square this equation and solve it, okay, there is a big calculation for this. Okay, and if you extend this equation, okay, directly they have given, okay, so let me put it as this is not 4 pi, pi by 8, pi by 4. Okay, so pi by 4 into, okay, solving this equation, it will become 8 pi, no, 8a square, 8a square nu d nu by c square. Okay, if you cancel this, you will be coming out with a value of, okay, this will become 2a square nu, okay, by c square d nu. Okay, this is for the two-dimensional case. Okay, all are coming in square. Do you remember in Rayleigh genes, it will be AQ by CQ, because they have taken it in the case of three-dimensional. For two-dimensional, this will be only a square, because taking the length of the cube as a, it will be a square by c square only. Okay, now similarly extend the same idea to the three-dimensional case. Okay, imagine this figure was just n1 and n2 along x and y side. Okay, we assume that there are quadrants and there are circles. That is called, these points are called as the modes. Okay, wherever there is an intersection, we call it as the modes of vibrations. Okay, and then taking two concentric circles, we have calculated the area between these two first. Okay, so this is in a two-dimensional one, we have a square by c square. Okay, now extending this same thing into the three-dimension. Okay, then the number of modes of vibration, okay, extending it to three-dimension. You can cannot show it in the figure. You have to view it. It's like a sphere. It will come. Circle will become like a sphere. Okay. So it will become extending into 3 dimension. The number of modes. The number of modes of vibration within a frequency range of nu and nu plus d nu, okay, is equivalent to, in the previous case, we took the circle and we calculated the area for 2 dimension. In the case of 3 dimension, we need to take the sphere into consideration and not the area. Here it will be the volume, okay. The volume between the 2 concentric circles have to be taken, okay, is equal to the volume. Note it down, because it's going to be now sphere in the case of 3 dimension. In the case of 2 dimension, it is a circle and the area between the 2 concentric circles are being considered. Now, in the case of 3 dimension, it is the sphere that we are going to consider, and the volume lying between those concentric circle has to be calculated. Okay, note that point. Okay, is equal to the volume of the constant 1/8 of the spherical shell. Okay, underline this, spherical shell. Hope you are able to see this. Focusing is coming up with this or not, I don't know. Okay, is equal, or right? It's equivalent to the volume. Is equal to the volume of the 1/8 of the sphere. Okay. Similarly, I mean, these are the same thing as did before by Rayleigh and Jeans, not much change. Okay. Of the radii, again the radii is 2a nu by c and 2a nu plus d nu by c. Okay. These are the 2 radii and the volume of the 2 concentric circle. Okay. The volume that is lying between. So this radii is equivalent to this. Radii is equivalent to, I can say this radius is equivalent to 2a nu, and this is equivalent to 2a nu plus d nu, okay, by c, and this difference in the volume has to be considered. Okay, and when we take the sphere, okay, it's just 1/8 portion is the quadrant that we are going to consider. In the circle, it is 1/4, but in the sphere, it is 1/8. We are going to take it into consideration. If you take a sphere and cut and see, okay, 1 quadrant portion will be equivalent to 1/8 only. Okay, therefore we will divide the equation as, we will be dividing the equation by 1/8. Okay, and the volume will be, what is the formula? 4/3 pi r square, isn't it? So r squared is now r1 square minus r2 square. So r1 will be 2a nu by c the whole square, minus the other one will be 2a nu plus d nu by c the whole square. Okay, so then do all the mathematical part, and if you calculate it, it will become 1/8. Okay, 4/3 pi. Okay, into the, if you solve this equation, it will become 8a cube by c cube, which is constant, which will be taken outside. You are left with nu cube minus nu cube plus 3 nu square d nu. Okay, these 2 will get cancelled out. Okay, 3 and 3 again will get cancelled out here. Okay, 8 and 8 will get cancelled out. So you'll be left with 4 pi a cube by c cube, and here it will become nu square d nu. Right? These are the value that we will get it on the this one. Okay. So this equation is nothing but similar to that we got it in the Rayleigh genes. Then the number of modes of calculation is just similar to that of the way that Rayleigh used to calculate the number of resonator oscillating per unit volume. Okay. So here We know that A cube is nothing but the volume. So we can replace this equation, okay, as V into mu square also. Okay, either way. This way, or you can also keep it as 4 pi A cube mu square by C cube d mu. Okay, both are same. Okay. Therefore, I can say the number of modes of vibration inside a cubicle. Okay, so we have come to the end of this particular derivation. Okay, so the number of modes of vibrations. Okay, inside a cubicle enclosure with the frequency range of nu and nu plus du nu by c. Okay, or I can just put it as nu and nu plus d is equal to 4 pi. Okay, v square d nu by c cube, or it is 4 pi. Okay, c cube a cube by c cube d nu. Okay, log this equation. Okay, then now the last one is here. Since the black body radiations also is expected to travel with the velocity of light, okay, and are having a transverse nature. Okay, they have a transverse character in their vibrations. There are longitudinal waves, longitudinal types of vibrations, and transverse type of vibrations. You must have studied in your class 12, even in your first 2 semesters. Okay, the light and the sound wave portions. Okay, so since they have a transverse, they are expected. This C here, isn't it? The C is now considered to be equivalent to the black body radiation waves are expected to have the velocity as that of the light. Okay, and since we are correlating with the light, we are taking the transverse mode of vibration of the light here. Okay, so I can say, since the velocity of light, since the black body radiations are traveling with the velocity of light, okay, since the black body radiations which are traveling in the waveform are having the velocity of light c, okay, and are transverse in nature. Okay. There are transverse nature and longitudinal nature in the light wave traveling, propagation of light wave, isn't it? So they are considered now here to be transverse in nature. Okay. Okay, only one portion is being taken. Therefore, okay, hence the mode of vibrations, are double as that of the longitudinal vibration. Hence the mode of, okay, hence the mode of vibrations are double. Okay, in the case of longitudinal wave it is single, in the case of transfer wave it is double. Okay, double as that of longitudinal wave. Okay, if it's a longitudinal wave, we need not worry, but it is expected to travel, it is found to travel in the case of a transverse wave pattern. Okay, so therefore we need to multiply this equation because it's double, mode of vibrations are double as that of the longitudinal waves. Okay, the black body waves are supposed to travel in a transverse nature, so we need to double this to that of the longitudinal wave. So I put the term 2 here and I multiply here. Okay, so this equation will then finally will become 4 pi. Okay, I will put it always in this equation form. Okay, a cube by c cube d nu. Okay, so I can say that therefore the black body radiations, okay, in this black body radiations that are traveling in a cubicle container with the size A, okay, I can say the number of modes of vibrations. Okay, I can put this equation as the number of modes of vibrations. The number of modes of vibration per unit volume, okay, per unit volume, okay, within the frequency range of nu and nu plus du nu is calculated to be equivalent to 4 pi aq by c square into d nu. Okay, hope you have understood it. Okay, I will repeat just. Okay, now we have started with the calculation of the number of resonators per unit volume within the frequency range of nu and nu plus d nu. Okay, by initially taking with respect to n1 and n2 as in 2 dimension with a circle, and we try to calculate the area of one quadrant. Okay, and with the similar analogy we try to expand the same thing with the 3-dimensional with a sphere, and we try to calculate the volume between the 2 concentric circles of nu and with the radius of nu, frequency nu, and another one is 2 nu, 2a nu plus d nu. The first one was 2a nu radius by c, other one was 2a nu plus d nu by c. Okay, and then we try to find the difference between these two and the volume, and we have calculated that this was the final value as 4 pi aq by c cube and nu d nu is the number of modes per number of modes of vibration per unit volume within the frequency range of nu and nu plus d nu. Okay, so I will conclude this class with here. Okay, there is another, this is the first part of calculating the number of resonators or mode of vibration in a unit volume between the nu and nu plus d nu as calculated by Max Planck. Okay, this is almost similar to that of the Rayleigh-Jeans way of calculating their number of modes of vibrations or frequency within a particular radii. Okay, radius. Okay, similar. This both are same, and the equations are also same. Okay, this is the first half, and the second half is a calculation of the energy. Okay, average energy of the oscillator. Each vibrations are considered as an oscillators. Okay, with the particular conditions, and those oscillator are supposed to have a vibration with an energy, particular energy, and those energies are calculated, which we will study it in the next class, and in the next video we will try to send you. Okay, so I will stop this class here. Thank you for your patience hearing.